Hello friends, good day. Today I will talk about application of Bayesian inference in data science. Let me start with introduction. Bayesian inference is a handy statistical method that helps data scientists update the likelihood of a hypothesis as new data of information becomes available. So given the data, what is the probability of something being true? What is the probability that null hypothesis is true? Based on Bayes' theorem, it offers a strong framework for making probabilistic predictions and is commonly used in fields like machine learning, artificial intelligence, and data analysis. So this is the Bayes' theorem. Probability of an event A given and another event B. I change this. This is called posterior. So when a new data B happens, what becomes what turns out to be the conditional probability of A being true given B, and that I write as probability of B given A, which is likelihood. Probability of B is the marginal and probability of A is the prior, that is our previous belief about the event A. So this is Bayes' theorem. Bayes' theorem is a method for determining a probability when certain other probabilities are known. Named after Thomas Bayes, who introduced it in the 18th century, the theorem provides a way to update the likelihood of a hypothesis based on new evidence. Bayes' theorem assists in updating the probability of a hypothesis, an assumption you think might be true when evidence is presented. So given the data, what becomes the probability of an event? This means that you can refine your understanding and make more accurate predictions as you gather more information. Likelihood of rain today. Imagine you want to estimate the likelihood of rain today. You check the weather forecast, which indicates that an 80% chance of rain if dark clouds are present. Observing dark clouds in the sky, you begin reassessing your situation. How confident should you be that it will indeed rain? So here comes, so we need the likelihood, which is the likelihood of rain today. We have a prior belief, prior probability. This represents your initial assumption before encountering the new evidence. For instance, you typically consider that there to be a 30% chance of rain for any given day. Next comes the new evidence, which is likelihood. This is the recent information you have acquired. According to the weather forecast, if dark clouds are observed, there is an 80% chance of rain. And you update your belief, which is the posterior probability. You now integrate your prior belief with the new evidence. Given that you see dark clouds there and are aware of the forecast predictions of an 80% chance of rain in such conditions, you revise your belief to think that rain is now more probable today. Some mathematical framework. So we have let's break down the mathematical framework of Bayesian inference with a simple example. Assume we want to determine the probability that a patient has a disease given a positive test result. So D is the event that the patient has the disease, T is the test is positive, that event. So we are interested in probability of disease given the test is positive. So we have some prior idea about the disease. This is our initial belief about the patient's probability of having disease before considering the test result. Likelihood is probability of positive test given the disease. This is the probability of the test being positive given the patient has the disease. Marginal likelihood, probability of test being positive. This is the total probability of a positive test result considering both the cases where patient has disease and does not have disease. So we apply Bayes' theorem, we find the probability of disease given the positive test result. We turn it to we turn it to the likelihood probability of positive test given the disease into probability of disease by probability of positive test. So that these numbers give me the result probability that the disease is there given the test result is positive. Okay, so we have the prior probability of disease, which is 0.01. The likelihood of probability of test is positive given the disease is 0.99. The probability of a positive test result for a healthy patient is 0.05. So if we apply Bayes' theorem, we get probability of disease given the test result is near 0.2, whereas probability of having not disease given the test result positive is quite high. This is quite paradoxical, but this comes out from Bayes results. So there are some measure of goodness of our prediction. Sensitivity, also known as recall or true positive rate, measures the proportion of actual positive correctly identified by the model. Sensitivity is particularly important when cost of missing positive cases is high, such that medical diagnose. For the previous example, is probability of test is positive. So this is sensitivity or recall or positive rate, which is a measure of goodness of my prediction. And these types of things happen because the data is imbalanced. The probability of having the disease is very, very low, 0.01. So because of imbalance of data, this paradoxical situation comes up. Specificity, also known as true negative rate, measures the proportion of actual negative correctly identified by the model. It is particularly important in situations when cost of false positive is high, such as spam detection for certain medical screenings. So we want to get hold of uh, sensitivity, which is true positive rate, and also the specificity, which is true negative rate. Proportion of actual negatives correctly identified by the model, that is true negative rate. Some applications in data science, A/B testing, Bayesian methods are particularly powerful for A/B testing because they allow for continuous results updating and provide a more intuitive interpretation of probabilities. We want to evaluate the effectiveness of a new feature B compared to the existing feature A on a website. The goal is determining whether feature B leads to a higher conversion rate than feature B. So that is called A/B testing. We can use naive-Bayes method there. There is a naive-Bayes classifier. The naive-Bayes classifier is a simple yet powerful probabilistic classical classifier based on Bayes' theorem. It assumes independence between the features given the class level. This assumption is rarely true in real-world data, but the classifier often performs well despite this. There is an assumption of independence which is rarely true, but if we assume it, then this naive-Bayes classifier has a high success rate. Then Bayesian networks. A Bayesian network is a smart map that show how different things are connected and influence each other. Imagine you have a group of friends and you know who likes to share secrets with whom. A Bayesian network helps you understanding how a piece of gossip might spread through your group, or how an epidemic is spreading out in a population. The network contains nodes, arrows, conditional probability tables. Forecasting. Bayesian time series forecasting involves Bayesian statistical methods to predict future values in a time series. We will use a simple example to forecast monthly sales data using a Bayesian approach. Applying the Bayesian method with time series forecasting quantifies the uncertainty as a full posterior distribution of predictions, not just point estimates, which allow robust handling of uncertainty in predictions. So forecasting has an application of Bayesian inference. Conclusion: Bayesian inference is a key concept in statistics that allows data scientists to create and refine probabilistic predictions with new information. Understanding Bayes' theorem sharpens analytical skills, fostering more accurate and data-driven decisions. This entire talk is based on this blog, Practical Bayesian Inference for Data Scientists. I'll stop here. Thank you.